Great. Now we're on to our next speaker. This next talk is about JetReconstruction.jl.
So, quick talk about jet reconstruction, and first of all, thanks to the many people who've contributed to this talk, and I think that's actually one of the big changes between the talk last year and the talk this year, is that we now have many more people contributing to the package. What are jets? Because I guess not all of you are high-energy physicists. This is an event display from the ATLAS experiment at the Large Hadron Collider, and essentially these two cones that you see here are jets, where you have a high-energy particle that comes out of the collision point, and then it breaks up into many, many pieces. And the goal of what we do in jet reconstruction is to attempt to reconstruct what the high-energy origin particle is of all of these pieces. And that's really important, actually, for a lot of the things that we do in the physics that we're interested in at the LHC. Roughly what the algorithm is a sequential algorithm which takes these energy deposits that you can see on the right-hand side there, and it starts to merge them together until it finds what it considers to be a good solution for the way in which the energy is distributed. And there are various aspects to the metrics which are important, but basically you would continue this merging process until you reach a certain number of what you would call the origin jets, or you've merged all of the energy in one particular cone. This project started off in 2022 as a student project, just a kind of proof of concept. Can we do high energy physics algorithms in Julia? And we were so impressed with the results that we went ahead and we released a package about a year ago. So let me start by telling you about more physics goodness that we have inside the package since last year. Our initial algorithms were for proton-proton collisions. These are the kind of collisions that we get at CERN today, because that's what the LHC provides. And a next generation collider that we're imagining for particle physics would actually collide electrons and positrons. And this requires a different class of reconstruction algorithm for the jets. So we've implemented these E plus E minus jet reconstruction algorithms as well, and we're very happy with the results that Julia is basically 33% faster than our rival that's written in C++, which is called FastJet. So that's great. We can do the E plus E minus reconstruction, and we've also added support for what we would call the event data model, which is essentially the way in which these events are being produced. Here we took advantage of the fact that Julia allows package extensions. So normal use of the package, you don't need all of the extensions, but you want to read E plus E minus, it draws in everything that you need, which is really great. And we can actually reconstruct at 24 kilohertz on a single CPU core, which is extremely fast. We're very happy with those results. We also have extended the analysis that you can do inside of the package, because the core reconstruction is actually only the start of the process. What we're really interested in many cases is what's called the substructure analysis, where what you might reconstruct is what's in this big ring here, but you're interested in the little pieces which are inside. And so we've started to add algorithms which will allow you to do this kind of substructure analysis. And also, as LHC events in particular have a lot of pollution into the main event, we started to implement algorithms which can remove a lot of the unwanted soft radiation as well. So lots of techniques to skim the jets and to filter them, and in particular we've implemented the soft killer algorithm now as well. In the last part of the talk, I wanted to turn to our experience with static compilation, some more sort of Julia-specific things. The use case here is that we would like to perhaps use this package inside the triggers of the LHC experiments. And there, it would be quite important to have a statically compiled version, because the trigger is very latency sensitive and it can't afford any unexpected complications. So we've looked at both package compiler and JuliaC. I think I'll just more or less skip this slide, but basically to say that we've had a much better experience with JuliaC than package compiler is essentially what we would consider to be the future of the way in which you produce statically compiled objects from Julia. But having said that, it's not completely smooth sailing. We are looking at the results that we have here, and essentially the JuliaC version basically overlaps with the FastJet version, so we're no longer faster than the C++ version, whereas in the pure Julia version we are still a bit faster. We've essentially tracked this down to the fact that we have some extra copying overheads when we're passing the results back into C++. So we're at a good point, but yeah, it's not yet a completely convincing way of using the package. Compilation time is quite fast. In JuliaC, it's 120 seconds, and we get a 320 megabyte untrimmed library. We've not quite succeeded in trimming everything just yet. Package compiler is worse in runtime. It's about the same in terms of library sizes. Now, we have discovered definitely some gotchas with respect to the package. It turns out that data structures in Julia don't always map nicely into C. And because we have basically variable size chunks of data, we actually have to use variable size vectors, and they don't translate quite as well. The memory interface is definitely, there's a bit of friction there. It would be nice if we could just take a pre-allocated chunk of memory and fill it, but that's actually quite difficult because of the way that the package is constructed right now. Certainly, we've made some efforts to try and make the structures immutable. These were actually not too harmful on the Julia side to have these mutable, but on the C side, it definitely helps to make them immutable, so we've done that as well. We're scratching our head to think about exceptions because we can't trim the library and have exceptions as well, so we might have to change the way the error handling is done. And we've been battling away with trimming, and we fixed many of the problems that we had from our initial case. There's a backup slide on that. It's certainly quite a helpful exercise to go through. We discovered quite a lot of issues with type stability by looking at trimming, but we're not quite there yet in having addressed all of the problems that we have. And I think our conclusion is that if you want to write code that you anticipate using JuliaC for, you probably want to think about that very much as your use case from the outset, rather than trying to add it post facto. Okay. Running out of time, I wanted to mention one thing that we loved about Julia when we wrote this package initially was loop vectorization. Almost all of our speed boost over the C++ comes down to loop vectorization and using this turbo macro here. But because loop vectorization has a somewhat uncertain future, which makes us sad, we've been looking at alternatives for doing that. And it's quite difficult, and it's not making things easier for our code. So that kind of really aggressive, incredibly well-tuned Julia optimization we'd very much like to see continue. So coming to some conclusions, this is such a fast talk. The package is performing very well. We're improving the feature set driven by user requirements. We will actually have a 1.0 release very soon with a few API changes as well. We have new physics in the pipeline as well. Static compilation, I would say, is not quite production ready, but it's been a very interesting exercise to go through. And JuliaC is definitely the favored way of doing that in the future. And we'd love to have a new generic solution for our loop optimization problem.
Great. We have time for one question while the next speaker gets set up. Question? Okay.